You could hold off on the homework as long as you want. We don't mind.
I'm sure you don't know. That's why I'm pretty sure I've not been hearing any complaints. Okay, so now we're going to start going over propellant combustion. And so this is the same thing as a flame, but not for a gas, but for a piece of propellant or a piece of solid material. So here is just going to play some movies. Turn the volume up so you can hear it. So this here is a crystal of, get out of the way. This here is a crystal of ammonium perchlorate. If you recall from the beginning of this class, ammonium perchlorate is considered a very good oxidizer, and it's used a lot in rocket propellants. And so, but as basically one ingredient, as an oxidizing agent, but ammonium perchlorate will burn by itself. So if play the movie.
Ammonium perchlorate. This film reviews several reactions of ammonium perchlorate to temperature and pressure.
So you saw that nice, I'll play it again.
Ammonium
you see this nice burning front moving down.
Reviews several reactions.
The velocity that the surface is moving down is called the burning rate of the propellant. And so below the surface here, we have condensed phase material, would be ammonium perchlorate in this case. And then above the surface, you see we have some sort of gas phase flame structure. And for this particular case, it's actually becoming turbulent. Okay, and so essentially what we will do for propellant combustion in terms of studying is basically studying how this, studying this flame structure here. I'll be a laminar version of it, not a crazy turbulent version of it, and we'll be studying how the gas or how the temperature is coupled at the interface between the gas above the surface right here and the condensed phase material below the surface. And so there are all kinds of, now note there is no fuel or oxidizer, is that the ammonium perchlorate is its own fuel and its own oxidizer. And so basically, recall from the beginning of this class, when we discussed energetic materials, is an energetic material is a compound where at the molecular level, the fuel atoms and the oxidizing atoms, whether it be oxygen, chlorine, or fluorine, are bonded together in basically one big molecule. Okay, and so there are chemical bonds that are holding the fuel atoms away from the oxidizing atoms. But if you supply enough energy to it, you break those bonds. And now, after you start breaking the molecule apart, the fuel atoms and the oxidizer atoms are free to mingle and interact and react dramatically, like you see here. Okay, and so this is ammonium perchlorate. It's an ingredient that's almost never used by itself, but when you see big crystals like this, those are done in experiments and fundamental studies just to understand how ammonium perchlorate burns by itself. Because again, if you can't really understand how it burns by itself, you can't understand how it burns as one of many other ingredients. Okay, and so let's see another one. And so materials like RDX will also burn. Let's get out of the way. And so RDX here, what they have here is, I'll step forward. They have a little puck of RDX inside, or a small little cylinder of RDX placed inside of a little glass housing. And then they ignited it from the top, and you see a burning flame structure here. You see a traditional flame zone here and a sort of purpley region here. Those are just due to some of the excited species that occur within the flame structure of RDX. And then if you play it, you see the surface moving down. But if you look really carefully at the movie, you can't see it when it is standing still. but I'll play it again. When you watch the RDX surface move down into the sides, you'll see some bubbles and things like that form. So you see all those bubbles form just underneath the surface of the RDX while it's burning. So a lot of the pure materials behave in a very complicated fashion. Whereas with the AP, there did not seem to be any of this condensed phase bubbling and things like that. But in reality, there is enough heat supplied to the surface that you can actually start to boil the surface in some cases, or there are chemical reactions occurring within the solid material as it heats up, and then those provide enough heat to actually melt the material and even generate gas in the form of bubbles. And so I'm not going to have you do any homework with that, but I will go over a very comprehensive model for RDX that accounts for all of that stuff. And then you'll see how energetic materials and multi-phase processes sort of combine into a single nice problem where you have the combustion of, say, RDX, and you have multi-phase processes through you have a solid gas surface itself through the RDX gas interface right here, and also you have processes due to you also have a condensed phase bubble formation, and then bubble nucleation processes and growth processes, which are in the vein of more traditional multi-phase modeling. Okay, and so this here would be just a solid crystal of RDX. Wait, some more. Let's see. So this here is a movie that was made in a similar class that I took when I was at Penn State. They had access to an experimental lab with all sorts of fun stuff, and we had propellant day, and we burned things. And so this was to demonstrate, here we have a V block, and Steve Sun placed some C4 in that V block. And so this was to demonstrate that explosives can also burn, but they also burn really poorly. And so I'll play the movie, and he has a hot wire igniter system here. There, now you see the plastic explosive or C4 starting to burn, but it burns really pathetically compared to an actual propellant. So that's one thing to keep in mind, is that even though the base ingredients of an explosive and a propellant are almost the same, what makes a good explosive makes a pretty poor propellant, and what makes a good propellant makes a pretty poor explosive. In fact, it didn't even burn down very far into the V block, whereas a good propellant would have burned all the way down with fairly quickly and with no problems. Okay, and so that's just to highlight that even though HMX and RDX and a binder and all that stuff may be present in both explosives and propellants just due to the various processes involved, what makes a good explosive does not make a good propellant. And I've been asking people what makes a good propellant and what makes a good explosive, and you sort of get blank stares because they don't really know either, to be perfectly honest. So yeah, so you can't use them interchangeably. It's usually intentional, but it's usually extremely difficult to get a piece of rocket propellant to detonate, which is for obvious safety reasons. You do not want your rocket mortar to suddenly detonate if there's some sort of little pressure excursion or something like that. Okay. What else do I have? And so all of those would have been considered homogeneous propellants. And a homogeneous propellant, expand this. And a homogeneous propellant has a uniform physical structure. And so in the case that I showed you, the cases that I showed you, those were for the most part pure, basically pure materials, RDX or pure AP. Pure RDX or pure pressed pellets of RDX crystals, or a solid or a large solid crystal of ammonium perchlorate. Those are never used. Those are never used in practical in a practical system because they're too difficult to work with, but they are used for basic studies. But that doesn't mean that homogeneous propellants are not useful. In fact, they're used quite a bit in one application. And so what makes a homogeneous propellant homogeneous is that the solid structure of the propellant has a uniform physical structure. And for practical homogeneous propellants, they are usually made of a mixture of nitrocellulose. I'm going to use the acronym NC for nitrocellulose, which is a common one. Basically, nitrocellulose is just a nitrated cellulose structure. It looks a lot like cotton, but it burns very rapidly. And so because of these nitro groups that are attached to nitrocellulose. And then because it's a burnable cotton and it's used in guns, it's often called gun cotton, which you may have heard that term before in the past. Okay, and so homogeneous propellants are made of a mixture of this nitrocellulose. But again, that's gun cotton, or that's the sort of cottony type structure. It's not very dense. It's kind of fluffy, and you can't really, and it can't really maintain its shape well. And the energy per unit volume is also pretty poor because it's a nice sort of fluffy cotton. So what happens is that they mix this gun cotton with some other ingredients. The most common one is actually nitroglycerin. Yes, it's the nasty stuff. And there are a lot of other ones like diethylene glycol dinitrate, or degden is a common one. And these are energetic. And what these do when you add these to nitrocellulose, are actually cellulose in general, like a cotton swab, is that this nitroglycerin and degden are called plasticizers. And so what they actually do is they turn the nitrocellulose into a gelatin, and then while it's in this sort of like viscous liquid form, what you can do is you can actually cast these propellants into various shapes, and then they eventually solidify. And so the combination of nitrocellulose and this nitroglycerin or degden, or the plasticizers, give homogeneous propellants their sort of nice homogeneous properties. And now a term you'll hear is a so-called double base propellant. And those are homogeneous propellants that have nitrocellulose and nitroglycerin as the main ingredients. And then there are single base propellants. Those just have one ingredient. You could consider the AP crystal a single base propellant. And also most liquid propellants, you could consider a single base propellant. Like nitroglycerin, if you were to use that by itself as a gun propellant, that would be a single base propellant. Okay, and then, so what's nice about homogeneous propellants is that their structure is perfectly uniform, and they're castable, they are safe, and they don't have any solid particles in them. So because of that, they are typically used for gun propellants. And so if you've ever, I suppose none of you have ever seen a gun propellant except for maybe black powder. But in a big gun, the gun propellant grains some of them are about the size of your thumb. And they have all sorts of little thumb-sized, small little propellant grains that have all sorts of little holes, slots, and things like that that are basically drilled into them. And these sort of in these various shapes give the sort of amount of energy released as a function of time that is desirable for the gun. So for gun systems, which we sort of have a crazy schematic diagram of one down here, for efficiency purposes, you want to release the energy of the propellant as fast as possible to produce the high pressure, which then pushes the round out of the chamber or out of the cannon barrel. But if you release the energy too fast, you overpressurize the breech end of the barrel and you crack it, and then bad things happen. And so they need to be very careful to actually very carefully tune how fast or tune the energy release rate of the propellant as a function of time, so as to maximize the efficiency of the round without in a safe manner. And you don't need to make and avoiding the consequence of needing to make the barrel thickness like 6 feet thick to be able to take those kinds of pressures. And we will discuss internal gun ballistic models, but they are very complicated. So each of these propellant grains is sort of represented here. And so here you have some sort of, I don't know, howitzer round or something like that. And behind it, you have a fill of maybe grains that look like that, or grains that basically look like this. So in this chamber here, they fill it with a bunch of propellant grains, basically made of this homogeneous or typically a double base gun propellant. Then you ignite the system, and it starts burning from the igniter end towards from the igniter end towards the end here. And this is a really complicated multi-phase flow. For any of you who work with multi-phase flows, you can instantly recognize that even if we use so-called ball propellant or sort of spherical grains, this is a very complex flow. You have very densely packed powder here, can be at the packing limit. The pressure in here in a gun system can exceed 100,000 psi, so you have extremely high pressures. You have some of the grains will be burning, and they will be producing gas flow, and that gas flow will actually penetrate into the granular propellant bed here, and induce flow, and then heat up the grains, things like that. And so basically, models that describe this process are fairly complicated, because they need to account for not only the combustion processes of the propellant grains and the fluid flow of the propellant products as the chamber pressurizes, but they also need to account for multi-phase flow effects, such as heat transfer between the gas and the particles, particle collisions, etc. So these models get very complicated very fast, and due to the nature of, if you look in the literature of modern granular Eulerian granular multi-phase models, and we'll discuss those later, actually their history actually starts with gun propellant models. Even the most famous kinetic, even the more famous kinetic theory based models have their history in modeling gun systems, because those were one of the first traditional applications where engineers wanted to model granular systems that had very densely compacted granular powders. Okay, so are there any questions with the sort of really 10,000-foot overview of homogeneous propellants? And in terms of lecture, we will be putting most of our time on that, because again, you can model that and get an understanding of that a lot easier than a heterogeneous propellant. Almost the theoretical study of heterogeneous propellants, you almost always need a really advanced CFD code to do that. and there is one at UF, and that is Tom Jackson's. I think it's called Rockburn, or something along those lines. It's rock something. A Rockburn code that can actually handle heterogeneous propellants. But like those are very state-of-the-art calculations. Requires lots of to do them in 3 dimensions requires very big computers. Okay, and so now if there are homogeneous propellants, then that must mean that the other class of propellants are heterogeneous propellants. And so these are also called composite propellants. Okay, and what makes them unique is that they have a non-uniform physical structure. And so the reason, and then they consist of, at a minimum, some sort of oxidizing crystals, or oxidizing particles. Those can be small crystals of ammonium perchlorate, ammonium nitrate. RDX in the context of a propellant is an oxidizer. And then surrounding each of the oxidizing crystals is a fuel-rich binder. And the most common binder is called HTPB, or hydroxyl terminated polybutadiene. And so here's a schematic diagram from Poe's book of a composite propellant or heterogeneous propellant. We have a bunch of oxidizing crystals right here, and some small ones. And so so we have a bunch of oxidizing crystals there. And then surrounding that in this gap here is a fuel binder. And so, so this fuel binder basically gives the oxidizing crystal structural integrity and sort of holds them in place. And also, if the oxygen balance for the oxidizing crystal is positive, the fuel binder is designed to add extra fuel to it, so that the overall oxygen balance of the propellant is as neutral as possible, okay, which isn't always possible. And so here is just a schematic diagram of a composite propellant, and here's an actual cutaway view of an actual composite propellant. And so all these things here are oxidizer crystals. If I were to take a guess, it'd be ammonium perchlorate, and then this here, the black stuff, is some sort of binder. And then, so now a homogeneous propellant, when it burns, if you consider a 1D burning little strand of it, if you ignore any side flow and turbulence, it'll have a perfectly 1D flame structure. I'm doing a bad job of drawing it, but it'll have a perfectly one-dimensional flame structure. But now what makes a composite propellant complicated is that the flame structure is by definition never truly 1D, because these oxidizing crystals will burn differently than the fuel-rich binder. And you could consider that if you look at this picture here, where we have a schematic diagram of the flame structure, it's not a nice flat flame structure like you'd get for a homogeneous propellant, but it is very complicated. You have what are called diffusion or non-premixed flames. And a non-premixed flame is a flame that occurs when you have the fuel and oxidizer separated, and the flame occurs where the fuel and oxidizer meet. And so that's exactly what you have at every single interface between an AP particle, which is oxidizer rich, and a fuel binder. So you could think of, if there's enough heat to basically gasify the fuel binder, this region here is going to be very fuel rich. And if you add enough heat to where you're either burning the ammonium perchlorate or you're sort of vaporizing it, which I'm not going to use the term, don't ever quote me on that. That's a very bad term for ammonium perchlorate. But so if the ammonium perchlorate is burning with its own little flame, but the products of ammonium perchlorate are oxidizer rich. And so this oxidizer rich region will mix with this fuel rich region here to produce a very large diffusion flamelet, basically surrounding each ammonium perchlorate crystal. And so this structure here is inherently multidimensional, and how fast this propellant burns is not just dependent, is dependent on a lot of things. So not only the amount or the total amount of the, say, ammonium perchlorate crystal or the type of binder, it's dependent on the size of the ammonium perchlorate crystals. If you use large ammonium perchlorate particles, you'll get a different burning rate than if you use small ammonium perchlorate particles. And if you use a mixture of different sizes, you get, a size distribution of particles, you get different effects. And these are not well understood. To this day, there's still a lot of, quote, magic to making solid composite propellants work. And that's because the functional relationship between the size and size distribution of these oxidizing particles and the fuel binder to the burning rate response of the propellant is not well understood. And so it's still, for the most part, a lot of people just doing trial and error. Folks like Tom Jackson are doing great work trying to bring this branch of engineering into the 20th century, or the 21st century, I should say now. Okay, and so, and because there's a lot of sort of like magic and trial and error, a lot of these propellants, they're still very, the exact formulation of them is still very closed, even though they were sort of made 50, 60 years ago. Even a lot of explosives that were made 50 and 60 years ago, you can look up and find out what they are. But for propellants, you can't do that, just because they went through a whole lot of trial and error to get them to burn the way they want them to burn for their rockets. Okay, and so heterogeneous propellants often also use metal particles as additives. And because of all these solid particles that are present in a heterogeneous propellant or a composite propellant, to my knowledge, they are never used for gun systems. And I think the reason for that should be pretty clear. You do not want burning aluminum particles going down the barrel of your gun system. If, after you fire 100 rounds, you probably won't have much of a barrel left. And so that's why gun systems use homogeneous propellants that don't use any metal additives. They use nice, smooth, or basically nice homogeneous propellants, so you don't have any solid particles that can basically blown down. That can basically be blown down the barrel of your gun system and erode the barrel. I mean, there's enough erosion from the round itself. You don't need to add more from grit due to the burning propellant. Okay, and I do have some movies of burning composite propellants. I have a couple of them. Let's see. So this is a high-speed movie of a burning composite propellant. And I'll play it. This here will be the surface. And these little orange things are burning aluminum particles. So you see the surface receding down. You don't see much of a flame. That's just due to the choice of the propellant. But you see all these aluminum particles coming off the surface, melting, then lifting off and burning. And so this is a really complicated process. For a homogeneous propellant, you wouldn't see the sort of richness of physical phenomena with the melting and merging of these aluminum particles, them lifting off the surface and burning in a sort of standard droplet flame. And we will be discussing that in a few weeks, so you'd understand this process too. Okay, and so this is a really complex process. Really, really complex.
Hey, Professor, what's the purpose of adding the aluminum particles if they don't like disintegrate and add like that much energy as like the combiner?
The aluminum particles are added for multiple reasons. One, is they do add a lot of energy to the flow. It's just downstream of the propellant surface.
Okay.
And so in this case, they use larger aluminum particles, and those tend to burn far away from the propellant surface. But say if you use nano-sized aluminum particles, those burn right away, and they burn very close to the surface, and then actually modify the burning rate itself. But aluminum particles are used for basically multiple reasons. Is remember that aluminum will burn L plus H2O will go to H2 plus some number of Al2O3. So if you think about the performance of a rocket motor, or of the propellant in a rocket motor, that's usually given what's called a parameter called the specific impulse, and that scales.
Would it be possible to move the movie because we can't see what you're writing?
Oh, sorry about that.
Thank you.
So if you consider the burning of aluminum, it will burn with water vapor, right, to produce hydrogen and some amount of Al2O3. This is condensed phase. This is very light. This is a very light product. So if you look at the specific thrust, which is related to the performance of a rocket motor, that scales with the square root of the flame temperature divided by the molecular weight of the products. So what the aluminum particles do is they add chemical energy to the system. So they increase the flame temperature, but in their gas phase combustion products, they take a fairly heavy water vapor and convert it into very, very light hydrogen. And so they simultaneously increase the flame temperature and decrease the molecular weight of the products. And so both of those act to increase the specific impulse. And there's another reason that they're used, and that's for combustion instabilities, is that we'll go over this a bit with homogeneous propellants, is that a change of pressure or a dP/dT in the rocket chamber will modify the burning rate of the propellant. And it's possible that there are some frequencies where the burning propellant and the acoustics in your rocket system will actually couple, and the propellant and the burning and they'll couple, and you'll get into a sort of resonant mode where the combustion chamber of your rocket will produce acoustic waves. Those acoustic waves will then modify the burning rate of the propellant and increase it, which will make a stronger acoustic wave. That acoustic wave will bounce off the walls of the rocket combustor and then further increase the burning rate of the propellant. And this process repeats itself, over the span of 10-20 seconds, and all of a sudden your rocket is in 1,000 pieces. And so those are called combustion instabilities in rockets, and those are very, very non-desirable. And that's part of what there's a so-called SLS, the sort of Senate launch system. One of the reasons that the system is so behind schedule is that when they were building the solid rocket or designing the solid rocket booster for the space shuttle, that was a 5-segment rocket motor. There were just 5 segments that were basically bolted onto one another, and they worked their butts off getting the combustion instabilities solved for that system. Basically, once they get those combustion instabilities solved for a given system, they do not want to change it because it's very, very difficult. And so what the Senate launch system did, I actually can't remember. I call it that so much, I can't remember its actual name. But essentially what they did is to increase the thrust capabilities. They added another half segment. So it was so that was proposed to be a 5.5 segment rocket motor. It was based off the successful solid rocket booster for the space shuttle. And their hope was that all the nasty combustion instabilities that they fought for the initial for the space shuttle would just not be present if they added just a small half segment. Well, unfortunately, that wasn't the case. And then initially, when I was in grad school, this first started, and we had a project with ATK Thiokol, who was building them, and they were for about 2 years. Many research meetings with them were canceled. There were a lot of delays because there were sort of all hands on deck trying to solve the combustion instability problem for the 5.5 segment mortar, and that was unexpected, and it was very expensive to fix. And so that's part of the reason that the timeline in the budget for that program got way out of whack. And it's also a big, massive government thing, and then the timelines and budgets always get out of whack for those, no matter how well run they are. Okay, so did I answer your question? Probably a bit too much.
Yeah, you did. Yeah, it just looked like the aluminum particles weren't adding much energy because they were pretty solid after leaving.
Yeah, in this
propellant.
case, they're not adding much energy to the salt itself, but it's basically what they do downstream. So this is just a very zoomed in view of it. But typically, they want to use smaller aluminum particles so that they do add energy to the burning propellant itself. Okay, and I'll just show plug Tom Jackson's work. So move this over. Oop, got a small. Then move this over. So this is just a little presentation that I gave a few years ago on something. So this here on the left is a modern version of the same experiment that I showed you earlier in the movie. This was done by Alice Atwood at China Lake. It's a burning composite propellant, and it's aluminized, as you can tell. It's just a much more clean movie of basically what I showed you. And so you can see that there's a very complex multidimensional structure to a burning heterogeneous propellant. This here is a GIF made by Tom Jackson here at the University of Florida, where all these little black things are burning. I think they're AP, and the white is the binder. And he's just studying the effect of the size distribution and things like that. And he has this. And he has an internal code where he basically does simulations with that. Okay, so are there any questions with this, with just the basic concepts?
So do you consider that flame to be diffusion limited still, or?
You mean surrounding each AP crystal?
Yeah.
Yes, that is a mixing limited flame.
Okay.
Yeah, but I guess I'll move the movie back. But these sort of diffusion flamelets, they are physically very small just because the AP crystal is very small. Just because the physical distance that the fuel and the oxidizer have to diffuse to basically come together and meet and then hook up is basically very small, and so basically, yeah. And so basically for a composite propellant, you can consider that if you chose a control volume that was way up here, that basically all of the fuel and oxidizer would be burned to their almost equilibrium state, if you chose it high enough. Okay, it's only with these massive burning crystals that you see that that it takes quite a bit of distance on this length scale to burn the composite propellant. Yeah, and just bear in mind that this whole domain is not quite 2 millimeters wide. So this is very, very small, very small. Most of the AP crystals or AP particles that are used in composite propellants are on the order of tens of nanometers in size. So these are very small. Okay, are there any other questions? Okay, so now we're going to do a basic analysis. I did in the other combustion class, which I'm teaching in fall, I did a similar basic analysis for the laminar burning velocity of gases. And now I'm going to be doing a very similar analysis for homogeneous propellants. Okay, and so this here is just a picture from Kubota. And so what we are after with this thermal theory is we are going to derive the functional form of what's called Saint Robert's law, which states that the burning rate of a homogeneous propellant, and even a composite propellant also follows this law, is given by a coefficient times pressure raised to some exponent. And then what we're going to derive is this law, and then we are gonna, and then after you derive that, you can relate A to thermophysical parameters of the propellant, and N to the order of the gas phase chemical reaction mechanism. Now, this constant in the predicted N is way off of basically actual physical values, but nonetheless, this analysis that I'm going to go through, it's a very good fundamental analysis for understanding how these propellants burn. And so what we are interested in, what you're interested in a propellant system, whether it's a gun or a rocket or something else, or some sort of pyrotechnic, if you shoot off fireworks at the 4th of July, you are burning, some sort of black powder energetic material, like the sort of booster charges, where you have the sort of tube, you basically drop the thing in, you basically light it, it basically goes shooting out, and it sort of it disperses little things that blow up and sort of make colors. Those have analogies to a lot of energetic systems used by the Department of Defense. And so that's why sometimes you'll see some Lawrence Livermore researchers studying firework systems, because it is a way that they can publish the work they've been doing for many, many years in a fun and sort of open way. Anyways, so what we are after here is understanding what affects the burning rate of the propellant, or how fast the surface moves down. We are interested in understanding the flame structure. Your second computer project is actually looking at this for 2 propellants. One is nitromethane, and the other is an actual double base propellant. We are interested in the effect of pressure on this, because you could imagine that for a rocket, you can control the pressure via the size of the rocket nozzle. And obviously you sort of want to make the pressure as high as possible, but also you want to make it safe for your system. And also you want to make sure that the propellant doesn't do anything too wild. And so we need to understand how the propellant burns as a function of pressure. And so we can see at low pressures, and low for a propellant is 1 megapascal. We can see that we have, in this region here, we have pyrolysis gases coming off the surface. Then after a delay period, they ignite and burn to form a luminous flame zone here. And at low pressures, this distance between here and here is actually quite large. But now if we double the pressure, this distance here that it takes for these species here to ignite and burn, to form a luminous flame, is significantly reduced. And if we increase the pressure further, this distance here is basically even more reduced. And so while you can derive this from basic principles, in practice, how this RB as a function of P is determined is through experiments where they have a windowed combustion chamber. They burn, this is called a so-called strand burner. And then they basically will watch it through a window, and the combustion chamber is large enough that even if it's a closed volume, the mass of the propellant to the overall volume of the chamber is very, very small. So even if you burn all of the propellant, you're not going to change the pressure that much. And so they can essentially determine the burning rate of propellant as a function of pressure by just burning multiple sticks at multiple different multiple different pressures. And then after they do that, they will basically fit a functional form of this AP to the N type thing. And this is very common. And for a lot of propellants, you can basically look these up if they're publicly available. And for many of them, they are not. So, and here are some. So this is from Kubota. That is for this double base propellant. I don't know which one it is. He just called it a double base propellant. And so basically, if you expect a functional form like this, if you plot if you make a log plot of the burning rate versus pressure on a linear scale, A will be the y-intercept, and N will be basically N will be the slope of that line. Okay, and so here he's just when you are making a double base propellant, you can actually use different forms of nitrocellulose that have different enthalpies of formation. And so he's just sort of comparing those effects there. But basically, the key thing here is to note that for a lot of propellants, and on a log plot of the burning rate versus pressure, this will essentially be a perfectly straight line. For some propellants, they'll do some. I think I have a plot of that. No, I don't. For some propellants, they'll have a slope break, so they could look like this, and then there'll be a slope break right there. And then, when you see that, that's just due to a physical mechanism change. Is that there's something different that is happening with with the propellant. Okay, and so now we will look at the flame structure for a homogeneous propellant. So I just took the picture from above, turned it to the side. It's basically trying to burn back at velocity RB. And we have a whole bunch of different regions that you can identify here. So this region here on the gas phase, very close to the surface, is called the fizz zone. The fizz zone is where these gases that are sort of shooting off of the surface of the propellant are initially reacting. Those initial reactions are basically very, very fast. And then after those initial reactions, there is a sort of so-called dark zone where the products of these initial reactants are basically semi-stable. Is that they do burn with a lot of energy, but it takes some time to get them to ignite and burn. So in this region here, the gases of the burning propellant are just moving to the right. And in this region here, the gases are just waiting for enough time for them to basically ignite and burn. And then after they ignite and burn, we have a region here, and that's called the luminous flame zone. Okay, and so the gas phase region is divided, for a homogeneous propellant, is divided into a fizz zone. I don't know why it's called the fizz zone, it just is. A dark zone where there are essentially no chemical reactions, or they occur very, very slowly, and a luminous flame zone. Then in the condensed phase, there are two regions. There is a region here where the surface, where the solid material is actually hot enough to where you can have chemical reactions in the condensed phase. So those could be different solids turning into basically other solids. They could be different crystalline forms, like an alpha phase, like alpha RDX being converted into beta RDX, which are just different crystalline structures, or bubble formation, things like that. Those occur in a very thin layer close to the top, and below that is a region called the preheat zone. And basically here, all we have here is heat conduction, basically carrying heat from surface down into the propellant itself. Okay, and so, and I'll end it with this diagram here. But if I was to plot the temperature profile, here I have the condensed phase, which I draw in green. That's because one of the most common double-base propellants is green. And so this is the condensed phase region here. This here is the condensed phase reaction zone. This here is the fizz zone, dark zone right here, and the luminous flame zone right here. And so all put together, the temperature profile, which starts at some temperature T0 here, it will go up to the surface temperature, where the gas phase and the condensed phase temperature have to be the same. There will be an initial little bump up in temperature due to some rapid reactions occurring in the fizz zone. Then they'll basically taper off and achieve a sort of metastable state. But after a long period of time, they will eventually burn and then to produce the luminous flame zone. Okay, and so we will be discussing the pyrolysis species and then basically developing a small little model that will neglect the dark zone, a small little phenomenological model of propellant combustion. So that is all I have for today.
Professor, when we see in something burning on the end like that, is it always confined? Because I would expect that the propellant would want to run down the sides, like burn down the sides, and would that potentially run faster?
Yes, and what you're talking is a phenomenon called flame spreading. And in the experiments, like you saw, let me show the screen again. Like you see here, it's red. Propellants aren't red. When I helped out with the strand burner experiments in Ken Poe's lab, what they do to prevent the phenomena that you said is they actually painted the side of the propellant with a burning rate inhibitor. And that burning rate inhibitor, they use nail polish, to be perfectly honest. And so they would, we would sort of poke fun at them for going to JCPenney's, for going to the beauty section of JCPenney's to get laboratory supplies. Then you can see, and so that's basically, so there's a burning rate inhibitor that is preventing that. Because here, all we are after is just the sort of steady one-dimensional burning velocity. In real propellant systems, there would be a flame burning down the side, and you would need to consider that in your rocket motor analysis. And if you watch a movie very carefully with the AP, you can actually see that you can actually see that burning rate inhibitor. I don't know what it is for this crystal. It's something else. But you can see that burning rate inhibitor sort of peeling off to the side and sort of not quite burning away. But it is not, with the exception of inhibiting burning down the sides on the outside, it is preventing the burning. It is not affecting the burning of the propellant, which is why you see such a nice flat surface for this, is because of that burning rate inhibitor. And so you just see that sort of inhibitor moving out of the way and preventing the flame from basically propagating down the sides. And so, does that answer your question?
Yeah, it does. I was just making sure I understood that. And is it slightly concave?
It can be. I mean, when you do the experiments, you will never get a perfectly planar surface, but this here is a very clean surface. When I was helping the guys with the strand burner experiments, they would have killed to get a surface that flat. Normally, due to the non-uniformity of the ignition, they'll usually wind up getting a cup or a point. But what will happen is that point is you'll get a self-similar point basically burning straight down. And so you just basically pick the tip of the point or the bottom of the cusp and sort of pick that as your point to sort of work down. It's not ideal, but it's just the way, you know, the real world works for these things. This here is a very flat, clean surface. And again, they would have absolutely killed for that.
Okay, thank you.
Okay, are there any other questions?
Professor, is RB related to the laminar flame speed at all? Because they seem kind of similar in concept.
Yes, they are. RB is a laminar flame speed for propellants.
Okay, so it's just different like fields, different names.
Yep. Yep.
Okay. Okay. Thank you.
Yep. Yeah. And so, yeah, if you did a scaling analysis in, if you know that, you probably took combustion. If you did a scaling analysis for the laminar flame speed, the scaling analysis for the propellant burning rate is very similar. I'll do it differently than you may have done, but it is very similar with the exception that you assume that you can get the same result by repeating what you did for a gas phase laminar flame, but assuming that the gas phase density is not a function of pressure, and then you wind up with the same result.
Oh, okay, that makes sense. So it's just saying that it's incompressible essentially.
Yep. Yep.
Okay. Okay.
Yeah, and that's where a lot of the difference sort of comes in. And then because of that, you have to deal with this. You basically have to deal with this interface here. That's why we went over. That's one of the reasons we went over the interface jump conditions, is because you need to know how to handle that interface. Because basically, what you need to do even in the model that you guys are going to work on for your project is Cantera will handle the gas phase region, and you need a way to basically couple the solid region of the propellant to basically to the gas phase region. And so you do that through in that case, a clever control volume that includes way more than just the surface. But in most cases, the two are coupled by basically looking at the heat flux balance at the interface. Okay, and so basically all these interfacial boundary conditions and stuff, they may be kind of still a bit strange to you. But if you work in this area or multi-phase combustion, you're going to see them used a lot because you always have some sort of interface that that you need to deal with. Okay, are there any other questions? Okay, then have a good day.
Thanks, Professor. You
Yep.
too.
You too, Professor.
Thank you. You as well.